that one, Grandpa. I want that one.
It was something in church. Sorry, that was too far.
Any way you slice it, I'm either gonna get Brianna's back or Bethany's back.
Wait, Brianna's not here anymore.
Did she already leave?
Yeah.
Oh, yeah, she did. That's right.
Should Brianna go to dinner when she was away?
I'll get her back.
He did with you. Sit for Rachel.
Oh, yeah.
Sorry.
Oh, you did.
Oh, you say it? Nothing. I wonder if you're going to say, oh, yeah, you're listening or what?
No, I'm not gonna. I'm not gonna say, oh yeah, again.
You're just gonna get caught saying it once.
Yeah. Okay. I didn't beat them. Just because I'm in Maddie.
Maddie never even heard of Kool-Aid Man. You stole it from the Kool-Aid Man.
I didn't steal it from the Kool-Aid
Okay.
Man.
Oh,
I
yeah.
stole it
Right
that's
there.
probably the coolest
from
shit.
Vector from Despicable Me.
Oh.
Oh, yeah.
Well, he stole it from Kool-Aid Man.
Sorry.
Alright, ready again? Okay. Alright, welcome back, class. How are y'all doing? Okay, I have one important question. While you're scanning this QR code and going to that website, I have one important question. Do you guys like money?
Yeah, absolutely.
Okay. Would you guys be opposed to me giving you $1 million right now?
No.
Okay.
I'm one.
What if, okay, you could have $1 million right now, or you could have a penny that's going to double every day for the entire month. So let's say you get a penny on April 1st, it's going to double in value every single day. So what do you think you'd rather have, that $1 million, just straight up $1 million, or the penny that's going to double in value?
$1 million.
One penny? What's a penny?
A penny is one. How much are you gonna get? 45 cents.
Wow, it's pretty good, 50.
Oh.
Is that everyone? Okay, so more people are saying that they want the penny. Let's actually see how much that would be. Because it's fine to make like a guess, but this is a math class, and so we can actually find out how much that would be.
Wow.
So on the top of your guided notes, you'll see this table. Their notes actually has this mostly filled out because for time purposes. So I'm gonna give y'all 1 minute to fill out the remainder of the table, and we'll see where we're at.
Oh, thank you.
Yeah.
I was like, I knew she couldn't do that.
Last time.
Mhm.
Yeah.
We said we wouldn't do this, right?
All right, it has been 1 minute. Has anyone been able to get to the end of the table?
Yes.
And what did we find out? How much money do we have on April 30th?
5,368,709.12
Okay. So over $5 million. That's crazy how it went with, like, from 1 penny being that much money. How many? Raise your hand if you guessed correctly. All right, give yourself a round of applause real quick. Okay. So what actually happened here? We started with exactly 1 cent, and in a real class we would have gone through this entire table and you would have done times 2, and then times 2, and then times 2 over and over and over again, and that's kind of tedious. But is there some way that we've learned previously where we can, instead of thinking multiplying a number over and over and over again, is there a name for that?
With the
With
exponent.
an exponent. So I, instead of saying, I started here at April 1st, I did times 2 29 times. Instead of writing out times 2 29 times, I could just write, I have my 1 cent, and then times 2 29 times. And this is using exponents. And that's going to give us a nice segue into what we're going to talk about today, which are exponential functions. Okay. All right, so these are going to be our learning objectives for today. I'm going to get Nicole to read the first one.
The student will be able to graph exponential functions given the form f of x equals a times b to the x.
All right, thank you. Could I get Maddie to read the second one?
The student will be able to identify key features of an exponential function, including domain, range, y-intercept, and asymptote.
And then could I get Ingrid to read the last one?
The student will be able to solve real world problems by writing them in the form of x equals a to the power.
Okay, so if you notice, these objectives are very, very similar to what we did last unit. Last unit, we did graphing, we did key features, and we did real world problems, but for quadratic functions. Now we're going to be doing them for exponential functions. So a lot of what we're going to be doing is very similar, but it's going to be with a brand new type of function. And we're going to start off with some definitions. So, like our learning objective said, the general form is going to be f of x equals a b to the x. Now, if we think about our penny example was we had 1 cent, and then we had times 2, 29 times. Okay, so here, this looks a lot like this. We have a number up front, we have a number that we have a power to. So here, I can see that the 1 cent was my a. In our example, what was that 1 cent? That's what we started with. So, for the general form of our exponential functions, the variable is going to represent the, we call it the initial amount, which is the same thing as like our starting point. So we started with 1 cent, that's our initial amount, that's going to be our a value. And for our example, the times 2 is going to be the same thing as our b. And what we call that is the factor. So b would be our factor of growth or decay. So there are 2 different types of exponential functions. There's exponential growth and exponential decay. Based on what you already know about the words growth and decay, and our penny example, which type of exponential function do you think the penny example was? Was it growth or decay? Growth. Why do you think it was growth?
The number got bigger.
It got bigger over time. Our number was increasing over time. Okay, that's great. So we have 2 types of exponential functions. We have exponential growth, and that'll be when our b is greater than 1. And here, the function will be increasing. Exponential decay will be when our b is in between 0 and 1. Basically means it's going to be either a fraction or decimal. And for this kind of function, it will be decreasing. So in our penny example, our b was 2. That's going to be larger than 1. We were doubling every single time. Our function was getting bigger and bigger and bigger. And then we have one last vocabulary term. This is a brand new vocabulary term that we haven't done before, and it's called the asymptote. What the asymptote of the function means is the line it will not cross. So for any kind of function, the asymptote is going to be a line on the graph that our function will never cross. And that may not make a lot of sense now, but we'll be able to see what it looks like on an actual graph. Okay, so this should look very, very familiar. We've done very, very similar exercises with our quadratic functions. There's a couple differences. The big differences are over here. Before we had domain and range, and we had y-intercept, but now we have this thing up here that says growth or decay. Because there's different types of exponential functions, we need to see whether or not it's going to be a growth or a decay function. And then the last thing here is an asymptote. That's going to be our brand new vocabulary word. We're going to have to identify the asymptote of our exponential functions. And so, as we did before, the way that we can get our graph is by plugging in some points. And so if I have these x values, if I have x equals -2, plugging into 2 to the x, what should my y be, Nicole?
If we plug in -2,
Mhm.
that's gonna be 1/4.
1/4, alright. Oh, that's. Alright, thank you. Alright, Bethany, what should it be if I plug in -1?
1/2.
1/2? Okay. And then plugging in 0, well, if we have a 0 exponent, what's going to be the rule that we always have when we have 0 as an exponent? 1. So every time you see our exponent is going to be 0, it's always going to be 1. Alright, and these last two are more simple. Plugging in 1, I have 2 to the 1, which is just itself 2. And then I have 2 to the 2, 2 squared is going to be 4. So doing that, I have these 5 points that I can plot on my graph. So first I have -2, 1/4, and I have -1, 1/2, I have 0, 1, 1, 2, and 2, 4. And then once I've drawn all these points, I can do a rough sketch of the line between them. Alright, and that's what our graph is going to look like. Okay, just looking at this graph, remember our rules for growth or decay. When it's increasing, it's going to be growth. When it's decreasing, it'll be decay. So just looking at this graph, will this be an example of growth or decay? Growth. And then, based on what we already know about domain, what would be the domain of this function?
All real numbers.
All real numbers, yeah. It's going to the left forever and to the right forever. Okay. What about the range? Remember, range is all our possible y values. Do we have anything down here? Do we have everyone's there? No. The line that we don't cross is this line right here at y equals 0. My function only exists above that point, so my range is going to be y is greater than 0. Okay? Next is y-intercept, and we've done y-intercept many times before. Mackenzie, what would be the y-intercept of this graph?
0, 1.
0, 1. Alright. And the last part is our new vocabulary term. It's the asymptote, is the line that the function will not cross. And here, I already said before, it's going to be y equals 0. What happens here is, as this function goes left and left and left and left forever, it's getting closer and closer and closer, but it's never actually touching y equals 0. And the way that we often show that is with a dotted line at the asymptote. So if you ever see a dotted line on a graph that's saying it's an asymptote, that's saying it's a line that the function will not cross or touch. Alright. Did I get Mackenzie to come up here and do this example for us? Alright, let's help Mackenzie out by telling her the points. So what would be -2 if I plug in -2? Oh. Oh. Okay, there we go.
Hitting it. There you go.
So 16? Yeah.
So I think it's just yes.
It's 16.
Just
It would be positive, or it would be just 16. Yeah. Alright.
Yeah.
1, 4. Alright, perfect. Alright, yeah. And you're not able to show this one, it's gonna be awkward, but that's fine.
So we're just do this one.
Mhm. Alright, so this is just looking at this graph. This thing is going to be decay or growth? Decay. Yes, because it's decreasing, so we decay. What should our domain be? All numbers, yes. And unless for all exponential functions, it will always be all real numbers. Okay?
Y is greater than 0, and it's positive, y intercept is 0 and 1, and asymptote is y equals 0.
Sure.
Okay.
All right. Thank you. Give her a round of applause. All right. So I would go through a few more of these, having students come up and do them, just like that. But for time, we're going to move on to our next activity. All right. So around the room, you'll see different pieces of graph paper, and on them are your groups, and the names of the people in those groups. What you're going to do is you're going to go up to your graph paper with your group, and you're going to fill out a table of points, just like we did before from the equation. You're going to plot the points between them, and what you can do is you can check in Desmos, or your graphing calculator, which we've done Desmos and graphing calculators many times before. You can check your answers in those, and then you're going to identify each of the key factors of the function. So domain, range, y-intercept, and asymptote. And what you're going to do is one of you is going to fill out the table and do the graph, and the other one of you is going to identify all the key features. So I'm going to give you guys 2 minutes to go do that right now. In a real classroom, I would give them a lot more time, and that'll probably be multiple examples for them to do, and they would switch between each one. Like the first one would be graphing, the other one would be filling out key features, and then they would switch for the other ones and keep switching.
Yeah. I'm going to do the table on the graph or the key features.
Ready for this?
And this will be an assessment that will be collected at the end. I can collect all their graph paper and see their names on it, see who did what. And this is aligned to the objective of them being able to graph exponential functions and being able to identify key features, including the domain, range, y-intercept, and asymptote.
So you're going to do yeah, then just backspace. No, you would be because you just always start by you go negative 2, negative 1, 0, 1, 2. Like that's just the first. That's just the 5 points that are tossed generally.
Negative 0. Good.
You got to the instructions.
Yes.
Before. Would be the okay. Yeah, we do. That's good. This would be 1/2.
Got that nice graph.
So would be 2.
Yeah.
And then if you want.
Okay.
And I've got dry. And this is
32.
Over 16 times 1/2
And these don't have to be perfect sketches, they can be just rough sketches of what our graph should look like. They don't have to be perfect points for points.
And then that's 160. Awesome.
There's 1 point, so you want
Okay. And then domain.
0 would be
All of
and then 4
Because
is 1 is 2.
range. This y is greater than 0.
The same for all.
Y is 0, 2.
Couldn't have done it without that. Couldn't have done it without you.
Alright, I'm gonna give y'all one more minute to just finish up, and once you're finished, go back to your desk.
domain.
Good job.
Look at X, Y, Z.
That was good.
Wait.
Well, yeah.
F0. I didn't draw it on it.
Okay, let's begin making our way back to our desks. Alright, based on our activity that we just did, how comfortable do y'all feel about graphing our exponential functions and identifying their key features? Give me a thumbs up if you feel really comfortable on the side if you and then thumbs down if you have no idea what we're doing. Okay, we don't have any thumbs up. Okay, see, there is a generally positive reception.
Yes, to do that.
Okay, the next would be a kind of independent activity that we're not going to do, we don't have time. What I would be doing in a real classroom setting is I would be modeling how to solve this first problem, which will be, these are all of the real world examples of exponential growth and exponential functions. I would be modeling, for example, I would be modeling number one, I would be modeling how to identify A, how to identify B, and then how to put that in the equation and solve for it. And then I have them in their table groups do the rest of the problems on their guided notes. These ones. And this assessment would be geared towards the learning objective to be able to solve real world problems by writing them in the form f of x equals a, b, x. And so once they've done that, once they've been in their groups for however many minutes, they would tear off the back of their packet, which has all the problems on it, and they would turn that in and be able to keep the rest of the notes. Okay. So last thing we're going to do before we close up is we're going to scan this QR code and it's going to take us to a Jamboard. What we're going to be doing is I want you all to use your technology, use your resources to look up applications of exponential functions in real life and to include as many of them as you can on the Jamboard. Does everyone have the QR code?
Yes.
Okay. So I'm going to give you all 2 minutes to do that, do some research, post your findings, and we'll be able to discuss them for the remainder of the class period.
Whoa, who drew that? That would have really what?
The frowny face.
So I'm like trying to get it installed, but
Who's learned about? Who's in That's big.
Wait,
I
how did
did
you
not teach
see
me
it?
that.
Click the button. Thank you.
Okay, I'm seeing a lot of good ones. I'm seeing one that's kind of repeating. I'm seeing COVID twice. And yes, there was a major event in the history of the world that involved exponential growth. Because one very good example of exponential growth is a disease spreading through a population. As more people get infected with the disease, it spreads faster and faster and faster, and that creates that exponential growth where more and more people have it spread to them. Okay? Ooh, same thing with cancer cells. That's true also. Cancer cells also spread like that, and that gives us another example of exponential growth. Let's see. The depreciation of a car's value after initial purchase. Yeah, that's a good example. Loudness. Ooh, who said loudness of sound? Can you explain loudness of sound?
He said to Google it, so I did.
Mm-hmm.
And it said loudness of sound.
Does it have any kind of like explanation for why?
Fire. Didn't
Fire.
get that much detail.
Okay. We have so many great examples of exponential growth.
Just kidding.
So I thank you all for participating in this exercise, and that will be all.
Yes. Put it on.